This video shows the stability analysis using root locus techniques. The root locus is the locus of the roots of the characteristic equation by varying system gain k from 0 to infinity. We know that the characteristic equation of the closed loop control system is 1 plus g of s h of s equal to 0. The points on the root locus branches satisfies the angle condition. To know whether the point exists on root locus branch or not, we can find the value of k for the points on the root locus branches by using magnitude condition. The characteristic equation of closed loop control system is 1 plus g of s h of s equal to 0. The phase angle of g of s h of s equal to g of s h of s equal to tan inverse of 0 by 1, which is equal to 2n plus 1 5. The angle condition is the point at which the angle of the open loop transfer function is an odd multiple of 180 degree. The magnitude of g of s h of s is 1. The magnitude condition is that the point at which the magnitude of the open loop transfer function is 1. Rules for construction of root locus. Rule 1. Locate the open loop poles and zeros in the S-plane. Rule 2. Find the number of root locus branches. The root locus branches starts at the open loop poles and end at open loop zeros. So the number of root locus branches n is equal to the number of finite open loop poles p or the number of finite open loop 0 z, which is greater. Mathematically, we can write the number of root locus branches n as n equal to p if p greater than or equal to 0 and n equal to z if p less than z. Rule 3. Identify and draw the real axis root locus branches. If the angle of the open loop transfer function at a point is an odd multiple of 180 degree, then that point is on the root locus. If odd number of the open loop poles and zeros exists to the left side of a point on the real axis, then that point is on the root locus branch. Therefore, the branch of points which satisfies this condition is the real axis of the root locus branch. The rules for construction of root locus is shown in this graph. Rule 4. Find the centroid and the angle of asymptotes. If p equal to z, then all the roots locus branches starts at finite open loop poles and end at finite open loop zeros. If p greater than z, then z number of root locus branches starts at finite open loop poles and end at finite open loop zeros, and p minus z number of root locus branches starts at finite open loop poles and end at infinite open loop zeros. If p less than z, then p number of root locus branches start at finite open loop poles and end at finite open loop zeros, and z minus p number of root locus branches starts at infinite open loop poles and end at finite open loop zeros. Centroid equal to sum of poles minus sum of zeros divided by n minus m. The angle of asymptotes equal to 180 into 2q plus or minus 1 divided by n minus m. The asymptote with 60 degree angle and 180 degree angle and 300 degree angle is shown in this figure. The centroid is calculated as minus 2. Rule 5. Find breakaway and break-in points. If there exists a real axis root locus branch between two open loop poles, then there will be a breakaway point in between these two open loop poles. If there exists a real axis root locus branch between two open loop zeros, then there will be a break-in point in between these two open loop zeros. Write k in terms of ss from the characteristic equation 1 plus g of s h of s equal to 0. Differentiate k with respect to s and make it equal to 0. Substitute these values of ss in the above equation. The value of ss for which the k value is positive are the break away points. Rule 6. Find the angle of departure and the angle of arrival. The angle of departure and the angle of arrival can be calculated at complex conjugate open loop poles and complex conjugate open loop zeros respectively. Rule 7. Intersection points on imaginary axis. Substitute S equal to j omega in the characteristic equation and equate real part and imaginary part to 0 separately. The breakaway point is shown in this figure. Thank you.